Hello guys, I hope that you will be very fine this day. So today in this video we will be covering the different types of the labs according to the AVR tutorials. So in this first lab we will blink the LED using the Arduino IDE. Here you can see that the LED is blinking exactly the way we were supposing, even if you can just arrange it with the help of the 13th pin. So this is the hardware, and now we are moving on towards the software. Here you can see that we have to just go to the examples and then click the blink code, and then you will see that the code will appear right here, and just we have to just select the port, and after that we have to just upload the code on Arduino by attaching the port. So here we'll see that this is the Proteus circuit. Here you can see that we have to just upload the hex file that is being created by the Arduino IDE. After uploading a hex file, you can see that the LED is blinking successfully with some delay, because you can see that there are many delays in the simulation as well. So there is this was the work for this lab, and now we will move on towards the this is the LED blinking tutorial, in which all this lab has been covered, how to run it on Atmel, how to run it on Arduino IDE. So this is the Arduino code for the blinking on Atmel. So we will move on towards the Atmel, in which I will let you know how to create the C version file, and then upload the C code using the Atmel, and then we will see that how to upload the code of Atmel Studio on the uh, um, how to upload that code, and then you will see that we will just upload this code using the Xloader. And here we go. Here is the code for that. Now I'm just gonna copy here, and then you will see that this is the standard file that is named for the C program, and here you can see that we have included the avr.h, and then you can see that by running this program in Atmel, we have to just create the file, and then we have to just click on the C++ assembler or C assembler application, and then we'll see that we'll successfully compile. Now we'll see in the lab 2 task 3, we have to just take an input from the buttons, and then we have to just display the input that we're giving on the port from port C to port D. And you will see that when I will press the button, then you will see that the LED will be printing, or the input is printing at the particular port. For example, if I press the first bit, then the first bit of LED is turned on. If I press the third bit, then the third bit of the LED is print in the form of 1. So this is the lab 2 task 4, in which we have to just display the charging pattern on the port C or port D, whatever it is that we have to just display. And this is the program that we have created using the Atmel Studio by using the CDA and CBA commands. This is the lab number 2 and task number 5, and here we'll see that in which we have to just toggle the output pins. I have just not changed the number of the button, but when we will give the input, then the bits will be toggled. Here you will see that it is the 2 and 2 bits are working. Now you can see that the bits values is toggled, and when I release the button, then again you can see that the 1010 LED is being printed. Here you can see that the LED is being toggled. And this was the code for that. And now we'll move on to task 7, in which we have to just create the traffic light system in the Atmel Studio, in which you can see that the signals are just working like as if one green is open and the other are closed, and then you can see that the yellow light is opened, and you can see that it only one signal is opened at a time, and you can see that again after the opening of green LED, again so yellow LED turns on, and you can see that this is turned on. Now we will move on towards its code. Here is the code for the LED blinking, in which we have just used the CBI and SBI commands, mean that clear bit immediately and send bit immediately. So sending the bit immediately to the port will let us give the output in the form of that. This is the code for task 2, in which you can see that the LDI R register with the 0x25, and then loaded the data at R17 with the register of 34, and then you can see that we have just added the values and then printed it at the LDS, and we can see that added the register and then printed on the port C. So this is the core 2, and then we'll move on towards the core 3. In here you can see that R17 register is loaded with the 10 value, that is the decimal ones, and then here you can see that the R18 is loaded with a 0, and then R19 with 4. Again you can see that R18 and 21, and then decimal 16, and brne command just make us learn that if branch is not equals to, and then again means that it will jump to the again loop, and then output b is equals to 20, means that the port b is loaded with the 20 value. Again, if you can see the lab task 1, here you will see that this is the same as the above, but the decrement in the R25 register is being called, and we are just defining the loop to just from one saving the data from one port to the other. And then we will move on towards the next one, in which you can see that this is the task number 2. Here you will see that here the LDI means that the R16 register is loaded with the 8-bit value, and then again the port B is loaded with the R16, means that the value stored in R16 will be printed on the port B, and then again loaded the data on R17, then adding the data, the port C is loaded with the R17 register. Okay, and here you will see that we will move on towards the next code, in which you can see that the task 3 is being called, and then you can see that the loaded here the data is loaded with R18 with 0x00, means that we are just clearing the bit of this register. So here you can see that after giving 1, you can see that the LED pattern is just appearing like this, and giving the 0, you can see that the LED bar graph is completely finished. So here we will see that this was the report of ours, and then again moving on towards the Discord, that is especially for the charging sequence, and we have to just simulate it on the Atmel. Here you can see that a little bit delay is being called, and the SBI command is being used. So here you can see that in the charging pattern all the LEDs are turned on one by one, and when all the LEDs are turned on, then they will all get turned off. Again this process will be repeated. So here you can see that one by one all the LEDs are being turned on, and the delay means the delay function is being called below, in which we are just running the loops again and again in order to waste the time machine cycles that is being taken our time. So here we'll see that again in the every successive picture the LED get turns on and just giving us the output in the form of a charging sequence.
You made it through another day. You made it through another day. You did it, let's celebrate. Oh. Some days you feel you're brave, but you made it through another day.
Actually, this program is running very slow in the Proteus. Every program runs very slow in Proteus, so as you can see that the LED pattern is printing as our expectations, but it's really very slow, so that it's difficult to cover it in the entire video. You can see that the LED is turning off after every 10 to 15 seconds, but in the controller it turns very quickly. So here is the code for LED charging pattern, and now we will move on towards the task number 5, in which we have to take the two values at certain ports and then compare them. If both of the values are same, then we have to just print 0B1100100 on the third port, and then we have to print the 00110011 on the port if the comparison is not quite matching. So here you can see that is the code, and then we have to just see here that when the outputs inputs are just matching, then you can see that 11001100 is appearing, and then you can see that if we if the inputs are not equal, then you can see that the 00110011 pattern is appearing at the output as well. So here you can see that after equalizing both of the values, the LEDs get turned off. In this situation, we prove that it's working properly, and here you can see that the LEDs are again turned on if both of the values are not equal to each other. So this was the comparison task, and then we will move on towards the next task number 6, in which we have to just implement the following command and write the code in this function, comments about this function, what it is doing. So after just seeing that, we come to know that the R16 and 17 loaded with the particular values, and then you can see that the 16th register value is storing the addition, and then you will see that it is storing the values in the particular space, particular address, and then we will see that it is printing the output. And again we will see that this is the task number 7, in which we have to just create a traffic light system, in which here one by one every LED is turning on, and you will see that the how does it working means that SBI port D means that port D is being read, and the 0th, 3rd and 2 bit of the this port will be working for the red light. So you can see that first 3 red lights will be turned on. Again you can see that one yellow light and one green light will be turned on at the same time. So this is the code for that, and we will see that again we will clear the bits of the particular row in a traffic light system. Then we will see that this traffic light system will work properly when we have to just turn off the light. We will use the CBI command. This is a traffic light system, and you can see that these LEDs are just working like that. Here you can see that yellow LED is turned on, and after that green LED will be turned on. Here you will see that it's working properly. The red, yellow and green, this is traffic light system. uh, when the one LED is green, then all the LEDs will be, remaining three rows LEDs will be red. So this is the traffic light system. So it is taking some time to be executed, so we will move on towards the next experiment, or whatever you can say, lab task. So here is lab number 3, in which we have programmed to send 0 and FF to the port D. So you will see that from 0 to FF we will send the values, means that it is just working as a counter that will send the value from 0 0. So this was the task, and now we're moving on towards example number 7.3. Then we will see the code, and you can see that these LEDs are blinking after the particular interval. And if we just use the well, you can say that 7-segment display, then you will surely see the counting that is being from 0 to 100 exactly. So this is the just working as a counter that will count our values. Now this is the example number 17.14, in which we have to monitor the fourth bit of the port C. You will see that all the ports are not giving any change, but the fourth port is working as a port that will, means that if the fourth port is turned on, then the LED will be toggled. So here we will have to just take the input and check whether it is even or odd. Then we will see that if it is even, then blink the alternative LEDs, and then if the number is odd, then we have to just print the charging pattern. And here you can see that it's working properly. Now this is the lab task 1. Here is the proper documentation for that. Again, scrolling down and moving towards the example number 3.1, we will see that we have to just send the values from on port B from 0 to FF, means that 0 to 256. This was the code for the task that I have performed in hardware earlier. Here you can see that this is the C program, in which you can see that the unsigned character, and then storing it in an array and calling the loop at the particular value. You can see that every loop calling will increment every value, so this will be printed as an output on the port B in binary form. This is quite simple, it's not very difficult. So here you can see that this is the Proteus simulation for that, in which you will see that it's working very slow, but the LED pattern is just you can see that just doing like that, in which we can see that it's just printing the value in binary from 0 to 256, means 00 to FF. So again, moving on towards next example, you can see that we have to just write these ASCII characters. We have to just send these ASCII values to the port B, okay, and we will just store these all values into an array, and then after just writing it in the inverted commas, then you can see that it is automatically send ASCII values, ASCII characters or values, binary values to the port as an output. This was the counter. So here you can see that this is the example number 7.5 in which we have to write an AVRC program to toggle the bits of the port B 200 times. So here we will declare the port B as an output, and again you will see that and now we are giving the particular value to the port B, and then you will see that unsigned character Z is just given declared, and then we will see that from Z is equals to 0 to 200 the port B is toggling, means that again the execution of this for loop will happen and the port B will be toggled. So here we will move on towards the Proteus simulation. Here it is the code for that, and we will move on towards the Proteus simulation. And here you can see that this is the simulation for this, and here you can see that the bits will be toggled 200 times, but I have already told that the simulation in the Proteus is very slow, that it will take a time to toggle the bits, and you will see that the bits will be toggled. So here you can see that. Moving on towards the next file, and then you can see that clicking here, and then here we will see that we will move on towards the next experiment in which we have to just this is example number 4 in which we have to write an AVRC program to take a bit data from the port B and then send it to the port C. So here you will see that when we apply the toggle bit 1, then it should be directly transferred to the port C as well. And now here you can see that these are also in the pictures. You can see that 111 is transferred to the port C as well, and here you can see that with the help of the push buttons it can also be transferred to the port C. Now in example number 5 we have to run the following program and simulate, and we have to just comment it on the results. So you can see that the DDRB port is declared in the output, and now we'll move on towards the next one. You will see that all these ports are just illuminated with the LEDs, because in the previous code we are provided with a code that has no any input. All the 3 LEDs were working as an output, so we have disconnected it like that. By moving on example number 6, so in this example we have to write an AVR program to monitor the 5 bit of the port C as in the previous that I have explained you. Then if it is high, then print 55 to in hexadecimal to the port B, otherwise send AA to the port B. So we are just declaring the port B as an output, port C as an input, and then port D again as an output. So here the while loop is executing, in which the while 1 will means that it will run for forever. If the pin C is and this AND operation is being performed, means that the check the 5th bit. If it is high, then the 55 will be printed, and if it is low, then AA will be printed. So here we will see that a fatal error has been encountered, so we will move on towards the again uploading of hex file, and then you will see that the hex file is being successfully uploaded, and then you can see that it's now working properly. Again you can see that it's toggling. While going towards the report, you can see that AA and 5 is appearing as well when you can see towards the hex values. So now we will move on towards the next task, in which you will see that in the previous we have just performed it in the hard form, in which we have to just print if the even number is given, then print from lower to the most significant, least significant to the most significant, and if the odd number is detected, then print just toggle the alternative ports of bits of the port B. So you will see that the odd number has been detected, and now the LED pattern is just like from least significant bit to the most significant bit, and it's working very slowly, so don't be confused with that. And now we can see that if any of the odd number is being applied, then we'll see that the alternative is turning on. So here comes the conclusion, which we have to just focus on the ports. Now we will make a BCD 7 segment counter display that will count from 0 to 99. Here you can see that this is counting, and from 0 to 99, so the counting has been started. So we will have to make a program to operate an LED using a hex keypad. So now we will see that the hex keypad is working with that, and we will see that after pressing 2, the 2 is appearing at the output, and then pressing A, there is appearing at the output as well, and then you will see the 0, and then pressing the respective integer is appearing at the 7 segment display, where you can press the 7 segment display. Now we will move on towards its Proteus simulation and the codes as well. We will generally cover the introduction here, and then we will see the applications of the 7 segment display, how the hex keypad works, and this is the task 1, in which we have to just write the 8 mega program, in which we have to interface the 7 segment display with that as well, and this is the code for that. And you can see that we have defined the CPU and then LED directions, CDRB. And these are the standard libraries that we are defining here, and then in the main void function we will see that the LED direction will be the output, and the LED port 0xFF LED will be directional 0xFF, and LED port 0 means all the outputs are just declaring as an output, and then we will use the two-dimensional for loops in order to print the LCD at the port A with a delay of 50 milliseconds, and then we will see that this loop is executing multiple times for integers from I to 50 and then to 20, means that it will do nothing but this is the random delay that we are creating while destroying or wasting the time cycles, and then increment void function is again called, and then you will see that how the video ends. And now we'll move on towards its Proteus simulation. You will see that this is exactly counting as in the hardware, so it's just counting like that. We are wanting from 20, 21 to 22. The main thing is that we have to declare this for 2, and then the two-dimensional for this we will let both the sizes to be declared on this specific class. So it will run. So the counting has been finished. Now we'll move on towards the task number 2, in which we have to write the code to interface the hex keypad with X mega at mega 38p, means that it is the same experiment that we have just performed in the hard. Now we will see what it is in the code form. So here you will see that the CPU speed is also defined, and first you can see that the every single port of the port B is declaring as an output or input depending upon what we are wanting. So the DDR-C is again as an output. Then the port B has an array of three size, and then you can see that X of it has a size that will be printed, means that we are taking the input from the hex keypad and then we will print the output. And then there are the different types of the statements. So if if means that if we receive the particular value or the bit from the hex, then this will be printed at the output. So this logic will work to just create the interfacing of a hex keypad with the LED 7 segment display. So here the Proteus simulation comes. So you will see that pressing the specific button, the output at LED is appearing like that. And one of the most interesting thing about this code is that the code is 80% consisted of if-else conditions. Means we have to just perform the if-else condition in order to work it properly. It will not destroy our time. So now this is the code to display something on Arduino Uno or Mega, whatever we have. So this is the code for that, in which we have set the baud rate and then standard, including standard library, and then LCD string is equals to, oh my goodness, then you can see that this is being displayed, and then we will use the shift operation. Here we'll see that the shift operation is being used like this, shift string here, and then we will see that the string has been shifted. We will see the code, how does it works. So this is the task 1 for, in which we have to just interface the LCD, and we have to do the perform simulation just like as in the previous ones. So you can see that we have just included the standard libraries and CPU speed define a definition, and then we can see that define RS is equals to PB0. RW means that read, write and enable, and then LCD initialization means void, and then LCD data. This is the standard library for that is already predefined library for LCD. So you can see that LCD CMD is equals to 38 delay milliseconds. So this is the LCD init loop, initialization loop. And now we will move on towards the main function that can be used to perform the different tasks on LCD that we are just going to perform. Here you can see that void LCD MCD unsigned character function data type, and here you'll see that the AVRC code is just like that, in which the main C we have to add this, oh my goodness, okay, means that LCD initial init function is being called and then initialized, and now it is ready to be programmed. Then you will see that this is being printed. So in this experiment we have just only printed on LCD, but we have to just use the shift operation in order to shift it to the left. So this shift function is also pre defined. Now we will move on toward its Proteus simulation, in which you can see that so after uploading the hex file, you can see that I have just added 0 plus 1 is equals to 1, 3 divided by, again you can see that 3 is equals to 1. So this is the LCD interfacing with the hex keypad. The code is quite lengthy and it's difficult to explain right there in the video as well. So I will just give a little bit brief about that, in which you can see that The character temp three types of the characters and three types of the input operators are used means that I am just using the character means that let's suppose it is 8 plus 2 is equals to 10 means that there are three characters, that is temp1, temp2 and temp, and the input one will be the 8 plus 2 and then the operator will be OPR. Then, for example, if I am just storing these inputs and operating the temporary variable, then you will see that this work as a character and the DDRD port and B ports are working as an output ports that will go on into the LCD. And then you can see that here are the different types of the commands that means that after obtaining 00001 means that the first entry of the keypad is being pressed, so this all the statement is being constructed on the um, if else conditions, in which we will see the we will generate the code according to the hex keypad generated values, means if we apply 0000 and then what will happen, and then if we apply 00, so this is the for loop that will call in such a speed that we can't differentiate between the two means and extreme positions, but this code will run many times that any of one condition will be executed at the same time. So here you can see that it's working properly. Now we will move on towards the clock. So this is the clock. It means that the time is 2:38 and 35th of the second. Again, you will see that refreshing this, you can see that uh, this will work properly. And then again, moving on towards the next example. This is a real-time clock, but here you will see that again all the ports are working as an output. So this will let us and know that the A character unsigned character array, in which we have stored 0x3f, 0x06 and 0x5b according to the characters that we need an output. Here the for loops and for loops and for loops means that this will become the six dimensional, and then you can see that every execution of the loop will let the execution in the previous loop. So this is the lab task, last lab task, in which we are just interfacing the LCD with the Arduino, and then we will show the timer clock and then clock timers. Okay. In this we generally address the timer registers. This is the lab 6 and the task number 2, in which there are the two buttons, and then I will press every button, and the pressing of every button, the timer counter or whatever you can say, that the counter is counting its value, and it is counting at a very high speed, and you can see that the counter is overflowing, which can be seen with the help of a red LED placed right at the above finger. Here is the lab 6 and task number 3, the timer counter overflowing, in which we will check the timer counter and how many times the counter is being called and overflowed. We will check right there.
Hold on, head up, be strong. Hold on until you hear them come. Here they come, oh. Take an angel by the wings, beg her now for anything, beg her now for one more day. Take an angel by the wings, time to tell her everything, ask her for the strength to stay. sky. Oh, look up and don't ask why. Oh, just take an angel by the wings. Beg her now for anything. Beg her now for one more day. Take an angel by the wings. Time to tell her everything. Ask her for the strength to stay.